The morning session. It's a great pleasure to welcome Yoshiko Ogata at such a time. Thank you so much for joining us in the middle of the night. Her talk is the classification of symmetry-protected topological phases of one-dimensional Fermion systems.
Thank you very much for introduction, and thank you very much for giving me this opportunity to talk here today. I'm going to talk about classification of symmetry-protected topological phases of one-dimensional Fermion system. This is a collaboration with Chris Baum, who talked on Tuesday, and it's not brand new result, but 1 year old result, but I haven't had opportunity to talk about it so far, so I'd like to talk it today. And the problem is I barely remember what we did last time, so let me try. So about SPT phases, you already mentioned, you already heard about it several times, but our approach is operator algebraic. In the frame, we consider this problem from the point of view in the framework of operator algebraic framework of quantum statistical mechanics. So I would like to explain this framework first. So in order to do that, first I need to define what is ground state for us. So we consider unique capped ground state in this frame, SPT business, but what it is. So first, I would like to define what is ground state. And ground state in this framework is defined for dynamics, not for Hamiltonian. So dynamics means strongly continuous one-parameter group of automorphisms on a sister algebra. And let delta be a generator of this dynamics. And by state, what I mean by it is a positive linear function which is normalized. And a state omega on the sister algebra A is called alpha ground state if this strange-looking inequality holds for any element A in the domain of the generator. So that is a definition of ground state in operator algebraic framework of quantum statistical mechanics. And this is definition. And now we said that we are interested in unique capped ground state. And so first of all, we are interested in the situation that ground state is unique. So let us consider such a situation. So suppose that there is a unique alpha ground state, namely, suppose there is only one state which satisfies this strange inequality. Then let us consider such a situation. And then we say that this dynamics alpha has a unique gap ground state if there is a strictly positive gamma satisfying this condition for all this inequality for all A in the domain of the generator whose expectation value with respect to the unique ground state is equal to 0. So this is the definition, formal definition of a unique ground state in our framework. But if you have never seen these definitions in this framework, you may wonder why we have to think such a condition and what it is, the relation with our usual definition of a unique ground state. To see that, in order to do that, in order to see that, we can consider a very simple system that is n by n matrices, the sister algebra A being n by n matrices, and dynamics being given by usual Hamiltonian. Then if we consider this very simple system we are familiar with, and if we consider this condition in this system, then what we will find is that actually this strange-looking condition is exactly the definition, is exactly the same as our usual condition of unique capped ground state. So for this reason, we take this, so in other words, this is just another way of saying, of representing our unique Kaplan state in this framework. So for this reason, we take this as a definition of unique Kaplan state in this framework. And the reason why we do so instead of talking about Hamiltonian is because we don't have Hamiltonian in infinite system. So this is we take this as a definition in this framework. So in this talk, what I'm interested in is Fermion system. So it is Fermion system. It is a sister algebra called C-algebra over some Hilbert space H. But probably I don't need to explain about it for this audience. And for this C-algebra, there is an automorphism theta, which is defined like this. Which is defined like this. And clearly, this theta square is identity. As a result, this gives a grading on the CAR algebra. Namely, the CAR algebra is decomposed into direct sum of even part and odd part. Here, even part means the elements which are fixed under this theta, and odd elements are elements which get my extra minus sign when we apply theta. So this is CAR algebra, and we note that there is grading on the CAR algebra. Now, so it was the definition here was for any Hilbert space, but today what I consider is Fermion chain. So I take this H to be L to Z with T tensor Z to ZD. I take this Hilbert space in this talk. And we consider CAR algebra over this Hilbert space, and I call it a Fermion chain. And clearly, for each subset lambda, we can consider L2 space over lambda, and this tensor CD. And this space can be clearly regarded as subspace of this H. Therefore, the CR algebra over H lambda is naturally regarded as a subalgebra of a Fermion chain. So, and we do this. We always regard it so. And so this is our physical system. This is our sister algebra representing our physical system. Now, physical model in this framework is given by interaction. So let me define interaction. In this talk, I consider only even interaction. So even interaction is a map from the set of all finite subset of Z to the even part of the CAR algebra, satisfying these conditions. Namely, for each finite subset X, we assign some element phi X in this even algebra, but it has to be self-adjoint, and it has to be localized at X. Namely, it has to be an element in CR algebra over HX. So this is a definition of interaction. And we would like to make dynamics out of this interaction. But in order to do that, we usually need to require some some kind of locality condition. And there can be many such conditions, but the easiest among that is the finite range uniformly bounded interaction. A finite range means that there is some natural number m such that phi x equals 0 for x with diameter larger than m. And uniformly bounded means this, literally uniformly bounded. So this is a system and that is the interaction. And yeah. So having given some interaction, we can now define dynamics. In order to do that, we first construct local Hamiltonian, namely, so let phi be the given even interaction, and for each finite set, we define local Hamiltonian corresponding to this finite set as a sum of all the interaction terms inside of lambda. And this is local Hamiltonian, and then we take consider the Heisenberg dynamics with respect to this local Hamiltonian, and if our interaction is nice one, like uniformly bounded finite range interaction, then this limit is known. This lambda to infinity to z limit is known to exist for any each element A in the CR algebra, and it's and define a dynamics on the CR algebra. So like this, when interaction is nice one, like uniformly bounded finite range interaction, we get some dynamics, and that is a kind of dynamics we are interested in. So that is the dynamics, and now I'd like to move to this what is classification problem of gapped Hamiltonian without symmetry. So I would like to move to classification problem of such things. First of all, what I would like to classify is the following set. That is a finite range uniformly bounded even interaction with unique gapped ground state. That is a kind of interaction I'm interested in this talk. And we would like to classify them, and we would like to classify them in the following criterion. That is, two interaction in this set are equivalent, and I write like this. If there is a smooth path in this set connecting them. That is the definition of the criterion of the classification of a gapped Hamiltonian without symmetry. So actually this smoothness is a bit technical, and it requires these three conditions. So just briefly, let me explain. So let's say this path is parameterized, this smooth path is parameterized by 0, 1 interval. Then for each S and each finite, if we fix some finite set X in Z, then for each, we get, for each X, we get some matrix valued path, matrix valued function. And the first requirement is this matrix valued function should be unique. Should be smooth, sorry. And second one is about the expectation value of local observable with respect to the unique ground state. And it is as follows. First, note that for each parameter S, our interaction belongs to this set. So in particular, it has unique ground state. And I denoted this ground state omega by omega S here. So there is a path of unique ground state, and we consider the expectation value of local observable with respect to this unique ground states. Then we get some function. Then we require some kind of locality about so some kind of regularity about this function. So to describe regularity, we need a bit of preparation, so I would like to avoid it here, but if you are interested in, please look at this paper. And third one is so again, for each parameter S, our interaction belongs to this set. So there is some gap in the spectrum, gap gamma S in the spectrum between the lowest eigenvalue and the rest of the spectrum. And this gap should be bounded from below by some strictly positive value. That is the third condition. So this is a bit technical, and this is technical because we apply this theorem in the paper. But but anyway, we require this smoothness for this classification problem. But actually, this is physically totally natural condition, I think. So anyway, let us consider this classification problem without asymmetry. Then for this classification problem, Bon and Schutzbaldes and Matsui independently showed the following thing. That is, there exists a Z2 valued invariant for this classification. So so there are at least two different phases in this set of PUG. So this is a nice result. And then today's talk is about introducing on-site symmetry to this game. So today I introduce an on-site symmetry to the game. So let me first explain what kind of symmetry I consider. Probably you know, but I explain. Yes.
Can I ask a question about the previous slide? Is it now that this Z2 valued invariant is complete?
I don't think so.
Thank you.
Yeah. Okay. So on-site symmetry. So let me introduce on-site symmetry. Let's G be a finite group, and we also prepare some group homomorphism from G to Z2. And then I consider a projective and unitary or anti-unitary representation of G on CD relative to this group homomorphism P, which means the following. That is a U, which is a map from G to operators on CD. And this P group homomorphism decide if UG is a unitary or anti-unitary. Namely, if PG is equal to 0, it is unitary, and if PG is equal to 1, it is anti-unitary. And furthermore, it is a projective representation in the sense that UG and UH are proportional to UGH and with possible U1 phase. So we consider this kind of a projective representation. And as you know, when projective representation is given, this phase becomes a two-co cycle. Namely, it satisfies this condition. So yeah, and so we prepare some projective representation anyway. And then the symmetry, now I can tell you what is the on-site symmetry I consider here. We consider the symmetry given by action of G, which is defined by this equation. So here I'm identifying this L2 Z tensor CD with orthogonal sum of CD over Z. So we consider this kind of group action. So, so that is the symmetry I would like to consider in this talk. And we say that an interaction phi is beta invariant if each interaction terms are invariant under the symmetry. So now, what the object we are interested in, the object we would like to classify is the following set, that is finite range uniformly bounded even beta invariant interactions with unique abundance. So we considered now a subset of the previous class of interaction, and we care only the ones with which satisfy this symmetry. And we would like to classify them. And we would like to classify them with a similar classification criterion than before, namely two interactions phi 0, phi 1 in this set are equivalent, and I write like this, if there is a smooth path in this set connecting them. So the difference from before is that we require the symmetry to be preserved along the path. So this is a classification problem we would like to consider in this talk. So in this classification, because we do require the symmetry to be preserved along the path, it is by definition can be finer than the previous classification. So it may happen that two interactions are equivalent without symmetry, but they are not equivalent with symmetry, which bring us the notion of SPT phases. So that is a classification problem I would like to think in this talk. And the main thing I would like to tell you today is our result, that is there is an invariant taking value in Z2 and first group homology and second group homology. So that is the main thing I would like to tell you. I would like to devote my time for this. And of course, it's not we are not the first one to think about such a problem, and there are many famous papers on this subject, and based on Majorana chain or TQFT or Fermionic MPS. And our contribution here is that we carry it out in general setting. So with the rest of my time, I would like to explain how these guys shows up from our setting. In order to do that, I need very basic of operator algebraic theory, but as I understand that the audience can have many different background, so I would like to explain this very basic operator algebra theory. I apologize for probably many people. So let me do that. So first, what is representation of C-star algebra? Representation of C-star algebra is defined to be a pair of Hilbert space and a star homomorphism of from of A to B of H. Well, it's just representation. Maybe this part was not necessary. So so given representation, the strong so we take given the representation, I consider the strongly topology closure of this range of the representation. That become important for us, and I denote it by a W commutant of pi A and call it von Neumann algebra generated by pi A. So this strong topology closure become important in our analysis. Now that is that is just definition, and one basic theorem from operator algebra theory is GNS representation. This theorem says that for each state given, we can associate some representation of the C-star algebra basically uniquely. More precisely, let omega be a state on the C-star algebra, and then there exists a representation of A of the C-star algebra on Hilbert space, and there is also some special unit vector satisfying the following. That is, the expectation value of each of the observable is with respect to the state is given by this object unit vector and representation like this, like vector state. And another thing is that vectors of this form are dense in the Hilbert space. In other words, this omega, this unit vector is cyclic in the Hilbert space. And so there is such a Hilbert space, and it is unique up to unitary equivalence. So in our world, given a state, we can associate some Hilbert space representation of the sister algebra uniquely. Another thing, in order to define our index, implementability of automorphism in representation become important. So let me explain about it next. So let alpha be an automorphism on a sister algebra, and let h pi be a representation of this sister algebra. And we say that alpha is implementable by a unitary in this representation if there is a unitary on this Hilbert space implementing alpha in this sense. So we are considering adjoint of unitary here, and it's implementing alpha literally. So if there is such a unitary, we say alpha is implementable by a unitary. And what is good about the situation where we can implement the unitary the automorphism is that we can extend our alpha to von Neumann algebra. The closure is closure of the strong topology or topology or whatever closure of our range of the representation in the following way, in this way, sorry. So we define alpha hat automorphism on our von Neumann algebra by this form, namely by adjoint of U. So if you consider the case that this x is actually pi a, we get pi a here, and that become from here it is pi alpha a. So it's really this alpha hat can be seen as an extension of alpha in this sense. So when alpha is implementable, alpha extends to the von Neumann algebra. That is one useful fact. And so it's looks nice thing to have, but when such a thing can happen, actually we encounter such a situation frequently because of the following theorem. Namely, if our state is invariant under some automorphism, then the automorphism is implemented in the GNS representation of omega. So such a thing is known. It can be shown easily. And so if a state on a sister algebra A is invariant under an automorphism alpha on H, then on A, sorry, then alpha is implementable by a unitary in the GNS representation. Same for antilinear automorphism and anti-unitary U. So that is so when omega alpha is equal to omega, this implementability holds. And in fact, we encounter this situation rather frequently in quantum statistical mechanics. And for example, we already have that situation for our grading. So let omega phi be the unique Kaplan state of even interaction. And let h pi be its GNS representation. And our interaction is even, namely theta invariant. As a result, we can check that this omega phi composed with theta also is ground state. Namely, it satisfies that this also satisfies that strange inequality which was defining ground state. But now our unique ground state is unique, so this have to be equal to this one. So as a result, we end up with a situation we encountered in this theorem. So as a result from this general statement, there is this theta is implementable in the Hilbert space. Namely, there is a unitary gamma implementing this theta in the Hilbert space. And as I said before, a good thing is that this means that this theta extends to an automorphism by this form. And as a result, our von Neumann algebra, the strong topological closure of the range of the representation, it gets some grading. Namely, it can be decomposed to even part and odd part. It can be decomposed to the direct sum of even part and odd part. So that was example of the situation something is implementable, but it also includes some information I wanted to tell you that in our setting, our von Neumann algebra as well has some grading. So that was about implementability of automorphism. And another thing I would like to prepare is type 1 factor. So let me explain. First of all, a von Neumann algebra M is said to be type 1 factor if it is star isomorphic to B of K. B of K means a set of all bounded operators on some Hilbert space. And what is great about B of K is that we have Wigner's theorem. Namely, any automorphism on B of K is implemented by unitary on this K. The same for antilinear automorphisms. So that is very nice property of this B of K. And combining this, we can do following observation. First, let M be a type 1 factor. Namely, by definition, there is some star isomorphism from M to B of K. And now suppose that some group action is given, group action on M is given. Suppose that somehow such a thing is given. Then by this star isomorphism, we can encode this group action on M to group action of B of K. And this gives a group action, so this gives a group action on B of K, but now we know that group action of B of K is given by Wigner, by unitary or anti-unitary by Wigner's theorem. So by Wigner's theorem, this action can be implemented by unitary or anti-unitary like this way. So as a result, starting from group action on type 1 factor, we get some unitaries on Hilbert space. And because this one is group action, we have this this equality, of course, and of course. Then we replace this with using by formula with use, and this one become like this, and this one become like this. And this holds for any x in B of K. As a result, we conclude that this UGUH and UGH are proportional. Namely, there is some U1 factor satisfying this condition, which means that UG is projective representation. And as before, this theta this side is to cocycle, and when cocycle is given, we can we consider equivalence relation given by this boundary, and by taking quotient with respect to this equivalence relation, we get some second group cohomology, which I write here like this. Yes, so this little p here means that it comes from this beta g. I'm sorry, I didn't say. As before, pg is 0, then beta g hat is linear, and if it's 1, anti-linear. Okay. So now I'd like to come back to our original problem of finding this index. And as like most of work in this topological phase business, what is good to do is to look at the half of the system. And what is crucial, so let me denote the half of the chain by AR for the rest of the talk. And what is crucial for us is the following Matsui's theorem, which says the following. Let omega phi be a unique Kaplan state of even interaction with unique Kaplan state. Yeah. And let h pi be its GNS representation. Then Matsui showed that our von Neumann, the von Neumann algebra generated by this range of AR is either type 1 factor or a direct sum of two type 1 factors. So in fact, in this paper is a condition that translation invariance is required, but I can guarantee you that using original Hastings area law's proof and Matsui's proof from area law to split property, we can still show that this one without translation invariant. So anyway, this holds. And so there is some dichotomy corresponding dichotomy here in Matsui's theorem. And actually, this is the Z2 valued invariant found by von Schutz-Baldes and Matsui. So this is a very strong information, and our indices almost directly come from that. And so I would like to proceed to derive. So this part actually corresponds to this dichotomy part, which corresponds to this index, which is already found before. So I would like to derive this and that. So in order to do that, I would like to see this dichotomy a little bit more from the point of center, in terms of center. So first center of von Neumann algebra is that elements of in the von Neumann algebra we consider which commute with any other element in the von Neumann algebra. So that is center. So first dichotomy, the first one of the dichotomy is this one is type 1 factor, which means that this is isomorphic to B of K. So clearly the center is trivial, just a multiple of identity. And second one, it turns out that it's also it is two-dimensional. The center turns out to be two-dimensional, and it can be represented by odd of projection, like this form. So that you can show.
Odd with respect to the grading on the algebra.
Sorry?
Odd with respect to the grading on the algebra, right?
Yes, yes. I extended the grading to the von Neumann algebra, so there is grading of on the von Neumann algebra. Now I would like to further proceed And now I would like to look at the even part of our von Neumann algebra. And again, I would like to consider its center. The definition is the same. So the case 1, where our von Neumann algebra was type 1 and our its center is trivial, this center of the even part become a non-trivial, or it become two-dimension with and it's represented by some projection like this form. And second case is it was that it was a case that our von Neumann algebra is a direct sum of two type 1 factors, and the center was two dimension. In this case, actually, this even part is type 1 factor that you can show with a little bit of consideration. Now I can define, I'm almost ready to introduce what is this and that. So let us recall what our setting. We are considering even interaction which are beta invariant with unique Kaplan state omega phi. So let omega phi, let h pi be its GNS representation. And now our like before, we saw that because of the theta invariance of the interaction, the ground state is invariant under theta. The same thing happened here. Because of the beta invariance of our interaction, our ground state is beta invariant. And as a result, as we saw before, for theta, this beta g extends to the von Neumann algebra in the GNS representation, like this way. And furthermore, recall the definition of beta g was like that, and definition of theta was like that. So they commute. And for now, these commute. As a result, their extension also commute. From this thing, we see that this beta g hat does not move the even part of our von Neumann algebra. That's one observation we can have. And as a result, in other words, this beta g restricted to this von Neumann algebra defines an automorphism on this von Neumann algebra. So as a result, we got two group actions on to von Neumann algebra. So one is a beta g hat acting on this one, and another one is restriction of beta g hat to even part of the von Neumann algebra. And as is the case for any automorphism, this when automorphism is given, center does not move. So beta g hat moves the center of our von Neumann algebra to center of von Neumann algebra. Beta g hat moves center of even part of the von Neumann algebra to the center of even part of the von Neumann algebra. So that was a preparation. Then I can derive this index now. And so first of all, our von Neumann, let us consider case 1. Our von Neumann algebra is type 1 factor. And we have some automorphism, sorry, not here. We have some group action on this, our von Neumann algebra, which is type 1. And what we learned from before is that when there is a group action on type 1 factor, we automatically get second group cohomology class. That we learned, and we apply it here, and we get second group cohomology. And what is this one? This is just a group homomorphism from G to Z2. How we can find such a thing? It comes from this observation here. That is, beta G hat does not move the algebra. So the center of the even part of the algebra. And this center of the even part of algebra, it's given by this some projection W like this. It's two-dimensional. Now let us try to apply beta g hat to this omega. Then what kind of projection it is? It has to be belong to center of the von Neumann algebra because of this one. And it has to be projection, and it should not be 0, neither 1. As a result, the only choice we have is W. It should be W or 1 minus W. Let's decide that our number Qg is equal to 0 in the first case, and Qg is equal to 1 for the second case. Then you can see that actually this Q, a map from G to Z2, is actually group homomorphism, which is this one. And like this, we get the this index for case 1. The same thing happened for case 2. In this case, case 2, we get this second group cohomology by looking at this fact that this one is type 1 factor, and there is a group action on this type 1 factor. As a result, we get second group homology. And for this one, we look at the original von Neumann algebra, and we see that this, we note that this is this beta g hat preserves z. Therefore, the range of beta g hat is beta g hat z is either 0 z or 1 minus z. And like as before, we get first group homology. So we got some invariant taking value in the two first group cohomology, second group homology. We got some index, and we can show using factorization property of quasi-local automorphism, we can show that this is invariant of the classification. So that was my main thing I wanted to say. But before closing, I would like to make 2 remarks. So as I said, there are many nice papers on this subject before us, of course, and many of them have considered Fermionic MPS. And in our paper, we also derived Fermionic MPS out of ground state under some conditions. Namely, when we restrict our attention to some subclass of our interaction, namely translation invariant interaction, and the ground state density matrix has some uniform bounded rank condition, then we can automatically derive some fermionic MPS. And this kind of thing has been known for, was known for quantum spin system from a long time ago. But now we can do it for fermion system. Because of the grading, the representation get a little bit more complicated, but we can still derive something fermionic MPS. And second thing is that about these indices show some group structure when we consider a graded tensor product. So which may not be very surprising because graded tensor product is associative. But anyway, it follows some concrete group law, and it's a bit complicated, but yeah, we can see that. So, okay, sorry. Thank you very much for your attention.
Well, thank you very much. Nothing. Icon there. Any questions or comments, please?
I have a question. The same one than Emil's, because I didn't properly understand your answer. How about completeness of this invariant?
Sorry, I don't know. I don't think it's known. It's open problem.
And did you say that the Z2 invariant without a group action, you know it's not complete, or you believe it's not complete, or you don't know how to prove it or not?
I don't especially have opinion about it, but I don't. Yeah, I expect it's complete, but I just don't know how to prove it.
Okay.
There are several raised hands. Please, Blase, I apologize if I'm butchering your name. Maybe you can ask your question first.
Thank you. So an important role was played by the fact that there is this type 1 factor, which is isomorphic to B of K, and then we have had some actions, unitary, projective actions on this Hilbert space K, and I'm wondering whether this K is something that can be constructed explicitly. Does it have physical interpretation, or do we merely know that this exists?
Well, actually, our GNS representation is can be decomposed to left and right or something like that, and we are considering the right part of it. That is, this is K.
So
Physical interpretation, I'm not sure what to do. Maybe we should ask. Maybe we should ask some more physics.
But it comes from the GNS representation.
So, just to make sure that I understood correctly what you said, you take the ground state and you restrict it to the right portion, and then perform the GNS construction, and this gives you the Hilbert space K.
Yeah, no, that you can say that as well. Yes. No. Sorry. GNS representation itself is not the K itself, but just von Neumann algebra is the same.
Yeah, but it's in the same.
I mean, if there is no correlation at all between left and right, then you get K being equal to the GNS representation. But otherwise, it is not.
So just restricting the state on the right CAR algebra and going from there with the GNS representation will not do it?
It become isomorphic, so you can do that as well.
Okay, so but that's what he said.
Okay, sorry, I
misunderstood.
misunderstood.
Physically, if you start from the GNS representation of the whole system, and then you just produce excitations with operators on half of the system, you get a subspace. Now, that's, I believe, essentially the space you're talking about. But it's true that in some cases it's isomorphic too. Like if you have a product state, then you don't really have to make this distinction, but you can regard it as a subspace of the GNS Hilbert space that you have.
Yeah.
For the whole chain.
Yeah, generated by right part. Yes.
Giuseppe, you have a question.
Hi, Giuseppe and Daniel.
Hello, everybody.
Hello.
Hello, Yoshiko. Thank you very much for your talk. I'm Giuseppe Denitis. I have a very basic question. I think it's more a curiosity indeed. The very basic philosophy of your classification is that you define a space of states, and then you want to classify essentially these states by equivalents, which are homotopies. But you claim that these maps have to be smooth. And indeed, this is a topological classification, and you should need only continuity. Why you are requiring smoothness of these maps?
As I said, this is quite a technical reason. At the end, I wanted to show it is invariant. And to show it is invariant, we use some result for our result or some basic formalism in this capped business in rigorous analysis, and that require this smoothness. Sorry.
Yes. Okay. I understand. I understand that it could be technical,
Yeah.
but at the end, you expect that a classification by continuity is the same that a classification by smoothness. Usually, this happens for a very large class of spaces. You have a sort of Oka principle that tell you that you can every time extend the classification by smoothness to classification by continuity. I just wondering if it happened also in this case.
Yeah, I expect it should happen, but I think the analysis can be quite technical.
Yeah.
It requires some stability argument, I guess. So it's a bit hard, but a good question to consider in this framework, I think.
Okay. Thank you very much. Again, very nice talk.
Thank you.
Okay, we have a number of raised hands and zero time. Let me just consult with the chief. Emil, shall we just delay the next talk for a little while and continue the discussion?
Let's hear one question. Because Daniel, he had his
Yes.
hand for a long time.
Thank
Just
you.
so he's the most patient. So.
Thank you for the talk. I also have a basic question, which is maybe related to the question that was asked previously. Can you comment on pureness of these ground states? Are they ever pure? Are they sometimes pure?
Yeah, it's pure. Yes, it's because we are considering unique ground state. Well, yeah, unique ground state is always pure.
Okay, thank you.
Okay, thank you very much. I'm sorry to cut off the discussion here.